All right, so today we're hitting on trigonometry and inverse trigonometry, and we're hitting on exponentials and inverse exponentials, also known as logarithms. So hopefully the top row of this current screen looks familiar. Hopefully you've all seen these graphs of sine and cosine, tangent and secant. These are, remember, for sine, x here is the angles on a unit circle. When we're going around the circle, we're finding sine x. This is graphing it out on a line, so that these are called sinusoidal waves, based off the name sine. Sinusoidal, they move like a sine wave. Cosine is the same thing as sine, it's just shifted pi over 2 degrees. Tangent of x is sine divided by cosine. So everywhere cosine is 0, tangent x is undefined because cosine's on bottom. So like all the multiples of pi over 2 here end up being asymptotes on the tangent graph. And secant is 1 over cosine, so it's going to have the same asymptotes. I have something in Desmos that might be a little more helpful for you. This is the graph of y equals sine x from negative pi over 2 to pi over 2. And when we graph y equals sine inverse x, it looks like that. So sine is the red one, and sine inverse is the blue one. And if I drop the line y equals x on there, we can see that they are reflections of each other across the y equals x line. That's what makes part of what makes these inverse functions. The inverse, when you take the inverse of something, you swap x and y. And so that happens across the y equals x axis. And so we can see the tangent like that. And if we look at tangent inverse, it's like that. We still have the reflection across the y equals x. And cosine and s. I do not have secant here. Let me do this. Y equals cosine x. I want the full wave. We're going to do y equals secant x. Full wave. Come up here and turn these off. So there's our cosine graph. Everywhere that cosine is 0, secant can't exist. And so we end up with these asymptotes that they're not marked here. But it creates these things where like it makes they look like parabolas moving away from the cosine graph. The same thing happens with sine at its zeros, and that gives you cosecant. But we're going to be doing stuff with these. And this is on page 57 of the Anton book, if you want to look at the graphs later. I have sine x and sine inverse x on the sheet I'm going to scan today, and I have info on tangent. I didn't plot the tangent ones on the next page, but we have info on the tangent ones. If you are graphing them, I'll put the other screen back up where you can see a little bit better. Give you guys a quick minute to sketch them if you'd like. You know, Ainsley, I think you might be the only student that's ever taken me for 2 classes at once without ever having taken me as an instructor before. That's bold. That's some brave shit right there. Taking a teacher an unknown factor for 2 classes, that's like half your load this semester. She's getting a double dose of Hefe. That's insanity. My wife can't even take that much time with David. She's like, go to work. I didn't even know she had to say that. She's happy when I'm home. Give you 1 more minute and then we're gonna go on. Good morning, Justin. Sorry, I didn't see your message earlier. There's a reason we have to place limits on the lengths of these graphs. We can't use all of sine and all of cosine because the functions need to, for inverse functions, or a function to have an inverse, it needs to map 1 to 1. So you'll notice on the sine graph from negative pi over 2 to pi over 2, it starts at the lowest value of the graph, -1, and goes up to the largest graph at +1, but there is no repetition. We don't go back down and get any more below 1, and we don't go further to the left and get anything above -1. We're getting the full range of values there, so that when we do the inverse, it's also 1 to 1. Same thing with cosine. This darker graph is right here. We want it to be 1 to 1, which means it's got to pass the vertical line test and the horizontal line test. Vertical line test is what makes something a function. Horizontal line test makes it in where you can have an inverse. All right, let's get over to this. Quick reminder, you're gonna want to know the trig values. This pops up a lot. You do not want to be grabbing a calculator. So remember, we've got 30 degrees, 60 degrees, or that's 45, sorry. 45 degrees, 60 degrees, 90 degrees. The radian equivalent, in 0 degrees. We start, where's my pins? These measure the angle that is swept out from the x-axis as we go counterclockwise. The radian equivalent, to go from degrees to radians, you have whatever your angle is, theta degrees, and you multiply by pi over 180. And to go the other way, radians to degrees, you have your, I'll call it x, and it's 180 degrees over pi. So the radian values of these 5 points is 0. I'll do it over here. 0, pi over 6, pi over 4, pi over 3, and pi over 2. Yeah.
Failing to see how you get degrees to radians. What you multiply by something?
You multiply. So like if I wanted to go from 30 degrees to pi over 6, I'm gonna take 30 degrees and I'm gonna multiply it by that pi over 180. And this is 30 times 6. So my 30s cancel. And I've got pi over 6 left. I have some good resources in Canvas. For those of you that are a little rusty on your trig. Where the hell is it? Useful handouts. So there's a little stuff on it. There's even a blank unit circle you can practice with. I'm going to put a link in here because there's a video that she shows how to use the left hand, might be left hand. I think it's left hand. The left hand rule for memorizing angles. I need to add that link. What else did I want to say about this real quick before we start using them? Oh, this circle here, that black circle is x squared plus y squared equals 1. This is called the unit circle. The trigonometry equivalent of this is cosine squared theta plus sine squared theta equals 1. I'm cramming like a third of the semester of trigonometry all in like fucking 10 minutes. So this is hopefully just a refresher. Normally we have x equals r cosine theta and y equals r sine theta. That's the standard situation. For a unit circle, r equals 1. So this becomes x equals cosine theta and y equals sine theta. That's how we're getting the positions of that circle. These can also help you with where cosine and sine are positive or negative. Because hopefully, you know, when you're looking at the x and y axis, which values of x are negative, the ones on the left, and which values of y are negative, the ones on the bottom. So that's the same thing with sine, and same thing with cosine. Cosine values will be negative on the left half of the graph, and sine values will be negative on the bottom. Going all the way around the circle is 360 degrees or 2 pi radians. Radians are in fact unitless. We don't need to write radians. The only reason I'm writing it is so that you have it in your notes. but it's just 2 pi. All right, so those are the degrees and radians. Let's take a quick look at what their values are. Before we start that one, which is a practice sheet. Shit, that is not a straight line. Fuck it. Scratch that. That's sometimes you just gotta say fuck it and grab a blank page. Hopefully I don't fuck this one up badly too. Not the best freehand circle, but not bad. So we got 0 degrees, we got 90 degrees. We're looking at X and Y coordinates. So I'm going to write these. This is also looking at cosine theta and sine theta. I think. Yep, I was about to write on another piece of paper. So let's look at what happens as we go along the degrees, or again, hopefully a refresher. This is 0 radians, pi over 6 radians, pi over 4 radians, pi over 3 radians, pi over 2 radians. And now let's start looking at the X and Y values. They actually follow a nice pattern. Or theta here, we'll put theta there. And we've got X equals cosine theta, Y equals sine theta. Now that is not a straight line, but fuck it. That's what we're getting. 0, pi over 6, pi over 4, pi over 3, pi over 2. Okay, so for cosine theta starts at 1 and ends at 0, but that's not the way we're going to memorize it. I'm going to memorize this as square root of 4 over 2. Pi over 6 is square root of 3 over 2. Pi over 4 is square root of 2 over 2. Pi over 3 is square root of 1 over 2. And pi over 2 is square root of 0 over 2. Square root of 4 is 2, and then 2 divided by 2 equals 1. Square root of 0 is 0, and 0 divided by 2 is 0. That's fine. Square root of 1 is just 1, so this ends up being 1/2. And these values don't change. We don't have a nice simple value for square root of 2 and square root of 3. There is a pattern. This follows an easy to memorize pattern. They all have a denominator of 2. And they are all integer square roots. In sequence, there's no numbers even skipped. 0, 1, 2, 3, and 4 are represented. That makes it really easy to memorize these values. And we'll put them on the unit circle in a second. Sine theta just flips the order. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2. So that equals 1, that equals 0, that's 1/2. Okay, so recall this is a radius of 1. So this point on the graph, if I was not looking at trigonometry things, this should be 1, 0, and this should be 0, 1. Does that match up with our table? 0 degrees, 1, 0, and 90 degrees or pi over 2 radians, 0, 1. So that matches up. This one is root 3 over 2 and 1/2. The 60 degrees just switches the order of those. 1/2 and root 3 over 2. And 45 degrees, they both have root 2 over 2. Yeah.
Sorry to walk us back, but for cosine, or I guess for both of them, how do you get the root in the numerator? Where does that number come from?
It comes from solving cosine squared plus sine squared equals 1.
You just kind of have to know that.
Yeah, these are memorized values.
Oh, right.
And that's why I'm trying to show you the easy way to memorize them. It very much follows a pattern, and the pattern just changes order. And you don't get a much simpler pattern than that. 1, 2, 3, 4. All you gotta remember is the square root on it. You know, it doesn't get much simpler, but it is something to memorize. Thankfully, they change order, so it's not even like a different sequence between them. The rest of the circle you do not have to memorize if you remember where x and y are positive and negative. If this angle here is theta, then we will have the exact same values if we go the same movement away from the x-axis above or below. So what I mean by that is, notice this is root 3 over 2 and 1/2. If I move over to this side of the quadrant, x is negative over here. So this is going to be negative root 3 over 2 and 1/2. Below the y-axis, y is negative. So this will be positive root 3 over 2 and negative 1/2. And in this quadrant over here, both x and y are negative. So we'll have negative root 3 over 2 and negative 1/2. These are called the reference angles. So in all 4 of them, they are 30 degrees off of the x-axis. And the values are the same other than a plus or minus. That happens for any of these lines. I only drew out the 30-degree one, but the same holds true for 45, 60 degrees. And even the 0 and the 90. Which is fun. All right, that kind of recaps like the first 6 or 7 weeks of trigonometry course. We're gonna start using them. If you don't recall those, I'll bring it right back, but I just clicked on that blank unit circle in the module. This gives you a spot to write in degrees, radians, and their values over the whole circle. And when you've got this down to 5 minutes, you've got this down pat. You should be able to draw this circle with all its values in less than 5 minutes. It doesn't take that long to memorize. That's not what I wanted to do. And that was right there, blank unit circle. I'll show you a video that'll help, or I'll link a video that'll help. But she just shows you a way to do the same thing using your left hand. And she does it a hell of a lot better than me trying to explain it. She gets all enthusiastic about it. I just gotta remember how to find it. I'll put it up today, hopefully, maybe tonight. All right, are you guys ready for some practice? So now we want to take a look at finding these inverse values. So this might be helpful to remember how this works. Trig inverses. Maybe I should put up a blank page. Trig inverses. Normally we have y equals sine theta and x equals cosine theta. When we do the inverses, these swap. Theta equals sine y, and or theta equals cosine x. And when they're inverses, we say that. So this looks like an exponent. It is not. The -1 is not an exponent. It represents inverse. Where we're going with this is why I'm showing this is if you see cosine theta equals a number like we're going to have right here, √3/2. What this really asking you is, this is theta, that equals theta. So the equivalent of saying cosine theta equals that number. And that's an easier way to remember it. So when we do √3/2, we're really going for what angles does cosine theta equal √3/2? Okay. If we want to get the full values for cosine, this will cover all. Nope, that's sine. This covers all the positive and negative values of sine. So the possible values are -π/2 to π/2. This related to the graphs we saw earlier. And cosine, we get all the positive and negative values doing the top half. So theta for cosine has got to be between 0 and pi. I lost some brightness. Yeah.
The answer would have to be in the range from 0 to pi, right?
Yes, for the cosine.
So 11 pi over 6 would not be in that range,
Correct.
but pi over 6.
Pi over 6 is. That's right where I was going with that first question we're doing next. Exactly. So we want to know, this is the equivalent of saying, where is cosine theta equal to 3/2? Or not, I'm sorry, root 3/2. For normal cosine theta, this is pi over 6 and 11 pi over 6 as you go around the circle. But cosine inverse is restricted, so we're restricted to just that one. So this will be theta equals pi over 6 or 30 degrees. That's not helping. So we take a look at the next one. This one is saying, where does sine theta equal negative 1/2? Sine is negative in this region. And the one where the angle works, our degrees are restricted to these degrees for the inverse. So this is the region we're looking in. And 1/2 is related to the 30 degrees. So this would be negative 30 degrees or negative pi over 6. Not 330 degrees or 11 pi over 6, which is the theta equivalent if you go around the circle, but they're not in the domain of cosine inverse. Tangent theta has the same domain as sine theta for the inverses. So this also has the same thing. We are restricted. Our answers are restricted to these two quadrants. Tangent is sine over cosine. So one of them has to be negative. X is negative, Y is positive, or X is positive and Y is negative. The only spot that happens is in this region right here. X is positive, Y is negative. This is negative 45 degrees. Or negative pi over 4. So this is like saying tangent of theta equals 1. Find theta. Why don't you guys try D, E, and F? And see what you come up with. For F, I recommend when you do F, rewriting it as secant theta equals 2, switching to cosine theta, and going from there. If you haven't looked at the latest announcements, you probably should. The Mesa Center this weekend, or Friday, well, this Mesa Center this weekend, I'm gonna be there from 9 to 12, but on Friday, from 1 to 2, they have someone from Yale coming to discuss research on breast and ovarian cancer that they're doing at Yale, and how you can get a summer research position at Yale, how to apply for it. And that's in John Muir 124 on Friday from 1 to 2. There's a little flyer for it in the announcements. Whether you're male or female, breast cancer will impact your life at some point. If you don't get it, someone you know will. I don't know anyone that doesn't know someone, whether it's a family member or just a friend. Everyone's life is impacted by breast cancer, eventually. So it's kind of like, it'd be nice if they figure that shit out. I'm not a biologist or, chemist or any of that shit, but hopefully they figure it out. So I'm kind of curious what it is. I'm gonna be there. And after 1 to 2, I'm in the Mesa Center from 2 to 3, helping students before I go over and teach Seaside 2 at 3 o'clock. So if you go to the presentation, you can swing by Mesa afterwards and get some help on calculus. That's assuming you're free at 1 to 3 on Friday. All right, so how do we do on this? For D, what do I got to do on D? Who's feeling bold? Who's got the guts?
You have to go backwards,
What do you mean by backwards?
go down.
Go down?
Yeah.
So let's take a look at it. Cosine, this is saying cosine theta equals -√2/2. Cosine was when we covered the full values from the top. So it won't be down. It'll be left. Good try though. It's always worth trying. Yeah,
Is it, 3 pi over 4?
it should, let's take a look at it. Let's see. So this is just like straight pi or straight root 2 over 2 would be pi over 4. And so over here, one way of figuring out what that angle is it's backwards. Let me draw this a little bit bigger. It's backwards pi over 4 off of that line. This is pi, so pi minus pi over 4 is indeed 3 pi over 4. All right, let's do sine. What do I do for sine inverse equal or sine inverse of root 3 over 2? Yeah. What do you mean by quadrant? Like quadrant 1? Looks like it, right? So we're doing sine theta equals root 3 over 2. Sine is positive, and on our picture, sine is here, these ranges. So if we want positive, it is going to be in quadrant 1. What angle generates root 3 over 2 in quadrant 1 for sine?
60 degrees.
60 degrees or pi over 3. All right, secant. Who's bold enough to risk their name? Matthew, hit me with it.
So secant is just 1 over cosine, right?
It is.
So if you flip 2, that'd be equivalent to cosine. Be 1 over 2. It's equal to cosine. Right?
Yeah, so cosine will be 1 over 2.
Yeah, and then 1 over 2 or 1/2 of cosine is pi over 3 or 60 degrees.
Well done. That's correct. That's the easiest way to go about doing it. Do the secant. Remember, secant is 1 over cosine, or cosine is 1 at this point. So from here, you got like 1 over cosine theta equals 2, and you just take the reciprocal of both sides. Reciprocal. Or you recognize or remember this directly like that. I tend to do the reciprocal thing. All right, we're going to rewrite cosine sine inverse of x without using trigonometric functions. So we got some shit going on here, right? This is cosine sine inverse x. So a way to think about it is, let's make this a theta. Theta equals sine inverse x. And so sine of theta equals x. But sine of theta is SOHCAHTOA, opposite over adjacent. I'm going to assume x is positive here. So we're looking at an angle like that. Opposite is over here. not adjacent, hypotenuse. What the fuck am I doing? And what do I put here for the hypotenuse? If we don't have a denominator, we give a denominator 1. So how can I find, I want the cosine of that angle, so cosine of theta is going to equal, well, cosine is adjacent over hypotenuse. This side is the adjacent side of that angle. So I need adjacent over 1. How can I find the length of the adjacent side?
C squared minus x squared, right? So 1 squared minus x squared.
Yes, how are you getting that?
How am I getting that?
Yeah. You are, it's gonna be correct.
Yeah, it's just the Pythagorean theorem.
It's just the Pythagorean theorem.
Yeah.
It's exactly.
Yeah.
So we've got x squared plus adjacent squared equals 1. So adjacent squared equals 1 minus x squared. And so adjacent is going to equal square root of 1 minus x squared. So cosine of theta here, which is cosine of sine inverse of x, is just going to be adjacent over hypotenuse, which is just square root of 1 minus x squared. So you make a triangle, you figure out the missing sides, and then you go from there. It's gonna feel like a really fast day if you don't remember, or like a lot of shit today if you don't remember your trigonometry values. It's gonna be a hard day. Where you were correct, the side squared is 1 minus x squared. Most people aren't gonna look to it and jump to it, but everyone hopefully remembers a squared plus b squared equals c squared. A, B, C, a squared plus b squared equals c squared is Pythagorean formula. Hopefully that's something you guys remember. All right, you ready for some more pain? Let's bring on the pain. We are going to rewrite cosine of 2 sine, I should say sine inverse x. So we're going to do the same thing. We're rewriting without trigonometric angles. So I'm going to say theta equals 2 sine inverse x. This is a lot easier if I can write it as a sine theta rather than a sine inverse. So I'm gonna, first off, I'm gonna start off by dividing by 2. And I get sine inverse x equals theta over 2. And we can hit it with the old swap a root. Sine theta over 2 equals x. Now, this is the half angle formula. You probably don't have this one memorized. I had to look it up. In this situation, the equivalent of this is the half angle formula is x equals plus or minus square root of 1 minus cosine theta over 2. Like, you can't really use the Pythagorean formula to do the triangle thing because we don't have a regular angle in here, which is killing us. But we are looking for cosine theta because I defined theta to be the inside there. Theta was the inside. So if I can find cosine theta, I found what I'm looking for. So we just solved for cosine theta here. We'll square both sides. Squaring gets rid of the plus and the minus. They're both positive at that point. And we're just solving for cosine theta. So we'll multiply both sides by 2. And I get 2x squared equals 1 minus cosine theta. Subtract 1 from both sides. And if we multiply both sides by -1, we get cosine theta equals. Well, one way of writing it is just changing the signs and leaving them in order. The other way is like basically swapping their positions. 1 minus 2x squared. Either of those is correct. And so that is the answer. Not the equation part, because we wanted no trigonometric functions in it. So we wanted the equivalent of cosine theta, which will be 1 minus 2x squared. Couple other things I wanted to hit you with. Make you think. Does anyone need that up longer? Okay. If you need to take a 5-minute bathroom break, go ahead and take a 5-minute bathroom break. If I don't see anyone get up, I'm going to continue in a second. No point sitting here googly eyes at each other for 5 minutes. Yeah, someone's getting out. Like, pause the recording. So if you want a quick sheet on how to memorize your shit, take a look at this one. It's like the first page and most of the second page. You don't need the area functions or like the law of sines, law of cosines, although hopefully you remember them. But let's go back to what I wanted to talk about before we move on to logs and exponentials. One little more tidbit in this section. Let's say we have y equals sine inverse of 2x. Where is my black pen? There it is. So swapping these. The equivalent of this for sine would be sine y. And the left side is 2x. So x equals 1/2 sine y. That's another way of writing this. The inverse of this is y equals 1/2 sine x. So when you do the inverse, you just swap x and y. Why I'm bringing this up is the graph of this from pi over 2 to negative pi over 2 to pi over 2. Normally, sine does the full fucking thing. Sine does this shit. This is 1 and -1. And it does some shit like that. This is sine x. 1/2 sine x cuts that shit in half. The domain here is still negative pi over 2 to pi over 2. Notice the range is now different though. When you look at the range or the domain and range for what works for inverse sine, sine inverse normally has -1 to 1. Well, now the range is -1/2 to 1/2. So the range has changed. This is no longer the case. It's that. So if you have something inside, this started off as sine inverse of 2x. Having something on the inside changes what's acceptable out for your inverse shit. That was your trig bomb for the day. Hopefully the logs and exponentials doesn't feel as bad. But there is some formulas you hopefully memorize, already know. I'm gonna rewrite or give them to you again, just so you remember them. Give this another minute. I see some people still writing. All right. Next section. exponentials and logarithms. So exponentials are when we have the variable and the exponent. That's all exponential is. The variable and the exponent. So we generally write the generic form of the function as f of x equals b to the x. We want b to be greater than 0, and b equals 1 is trivial. 1 to any power is just 1, so it's meaningless. So we don't like using b equals 1, but any other base is good. And we don't want a negative 1 because then the value bounces back and forth between positive and negative as we raise those exponents. And this is not a graphable thing. So we want positive values of b. 0 is also a trivial case, so we don't include 0. So, as a reminder, the graph of b to the x in generic form sorry, I want 1 there, I want b here, I want negative 1 there. We got 1 there, and we got 1 over b here. There we go. When you plug in x equals 0, this is y equals b to the x. When x equals 0, anything to the 0 exponent is 1. So we have 0, 1 on every single one of these graphs. When I plug in x equals 1, we just have b to the first power, which goes like that. And when we plug in x equals negative 1, we get 1 over b. So the graph goes like this, where the y asymptote, or the x-axis is an asymptote. So it's continuing on its domain. It hits all the x values, but the range values are restricted to being greater than 0. So we don't include 0. We do that by showing the parentheses rather than a bracket. So parentheses 0 to infinity. Unless you're good with remembering how all the rules of flipping and translating and all that shit works for these, you're better off just putting in some numbers and seeing what happens. F of x equals 1 minus 2x. I'm going to do x, and I'm going to do 1 minus 2 to the x. 0 is an easy one to throw in. 0 is 1 minus 2 to the 0, which is 1 minus 1, which equals 0. So I will have the point 0, 0 on the graph. We should check negative 1 and positive 1. If I put in negative 1, I've got 1 minus 2 to the negative 1, which is 1 minus 1/2. Remember the rules of exponents, which equals 1/2. And if I put in 1, I've got 1 minus 2 to the first, which is just negative 1. If it helps you, do a couple more. Put in. I'm gonna jump to -5 and positive. Oh, I don't know that I can go +5. +3. -5 would be 1 minus 2 to the -5, which is 1 minus 1 over 2 to the 5th. 2 to the 5th is 2, 4, 6, 8, 16. 1 minus 1 over 16. So 15/16. This is almost 1. If I stick in 3, though, I've got 1 minus 2 to the 3rd power, which is 1 minus 8, which is -7. So when I get over to 3, we are way down here. Yeah. 2, 4, 6, 8, 16. No. 32 is the 6th power. So it looks like it's doing this. Over here, if we go further and further and further, I'm doing 1 minus something, but this 2 to the negative exponent keeps getting smaller and smaller and smaller. So I'm doing 1 minus a very increasingly smaller value. This is giving us an asymptote at y = 1. On this one, y = 1 is an asymptote. And it's directly related to that being the 1. A faster way of graphing this, if you're quick and comfortable doing it, graph 2 to the x, flip it over the y-axis, and then add 1. And I'll do that on an extra piece of paper in a second. I'll do that right now. So we're doing y = 1 minus 2 to the x. So if I graph 2 to the x, I'm going to just do it in dotted lines. 2 to the x has a point here, has a point at, so this is y = 2 to the x real quick, and 1/2. It's doing that. Y = -2 to the x reflects that across the y-axis. And if I want to do y = 1 minus 2 to the x, the only difference between this and this one is add 1 to all the points. So this point goes up to here. This point goes up to here. This point actually goes up to there. And our asymptote goes up 1 also. The asymptote was y equals 0. Now the asymptote goes up 1 as well. Add 1 for asymptote. And we'll connect our dots here and draw the curve. So that's might be quicker than doing the XY table. Notice I didn't need to do as many points. I didn't try like -5 and 3. I just did -1, 0, and 1. Those are really easy to do as exponents. Because they just give you either y equals 0 or y equals 1. Y equals the actual base that you started with, or y equals 1 over the base. That's the shorthand of that. E is E is considered the natural base. And we've all seen E before. But E is actually defined with limits. It's the, and I think I told you guys this in one of the beginning days. It's the limit as x goes to infinity of 1 plus 1 over x all to the x power. I don't know who came up with that shit. Someone far more clever than me. Seems like fucking pretty smart. Right? Someone probably researching, I don't know, the golden rule or some shit like that. I think the exponential E shows up in the golden rule or something like that. I don't know. You guys ready for more? Nope, I see people still writing. Yeah. Logarithms that we're doing next are the inverses of exponentials. There's a couple folks still writing this, so I don't want to yank it yet. All right, so how are these bad boys related? So that first sentence there is a really, really fucking long way of saying x equals b to the y and y equals log b of x are interchangeable. It says then for any positive value of x, log base bx, which we'll call y. This is that left part, log base bx denotes the exponent. So, ooh, I fucking just crossed it off. Denotes the exponent to which b must be raised to. So b to the y to obtain the value x. So that's the long way of saying that. What does that mean in terms of graphing it? when we had x and b to the x, we used -1, 0, and 1, and we got out 1 over b, 1 and b. When we have the log here, log b of x, these columns, since they're inverses, just switch. X equals 1 over b, x equals 1, and x equals b. And we get our y value equals -1, 0, or 1. This is true for all inverses. Anytime you have an inverse, you just swap the x and y values. So if you've made a table of x and y values, just switch the fucking columns. Okay? That's true for any inverses. So let's look at graphing this real quick. G of x equals log base 2. G of x equals log base 2 of 1 minus x. And rather than doing the x and y thing, which you can all do, and doing a calculator and shit, let's take a look at graphing log base 2 of x. What happens when we flip it, or what happens when we use the negative x, and what happens when we effectively add 1 to it. 1 minus x is the same thing as negative x plus 1. So we had 1 over b, or in this case 2, 1/2, 1, and then 2. 1/2, 1, and 2. Those are my related to my b's. Log base 2 of x, which we'll do in red, has a point there, has a point there, and has a point there. And its asymptote is the y-axis rather than the x-axis. In the last one we did like this, when we had a negative, it flipped it upside down. But the negative was on the outside of the function here. So when the negative is on the outside of the function, it flips it upside down or over the y-axis. When the negative is on the inside of the building, call's coming from inside the building. Instead of flipping over the y-axis, it flips over the x-axis. I said that backwards. It was flipping over the y-axis, now it's flipping over the x-axis. So we're gonna go the other direction here. And I'll do this one in green. We got this point, we got that point, and we got that point. Also in the last graph, we added the one on the outside of the function. And adding one on the outside of the function moved everything in the y direction one. Well, now we're adding shit on the inside of the function. And when we add shit on the inside of the function, rather than moving in the direction of y, we move in the direction of x. So here, that +1 is going to move everything to the right one because that's in the direction of x. So that point moves over here. This point moves over here. This point moves over here. And the asymptote also moves over 1. So our graph is going to be like that. All right. That's a recap of how to graph logarithms and exponentials. That's an algebra course shit, though. We're here for calculus. Actually, we still need to go over the properties of logarithms because that's going to be essential. I see some pins still moving, so I really need to try to be patient. We still got 20 minutes. I think I'm going to be making a video tonight for a couple of things I don't know that we're going to get time for. And if it's not tonight, it'll be tomorrow night. I'll get another video in though, I think. All right, so properties of log. Did anyone need that up still? Properties of logs. Those are worth writing down. So we want all of the values B, A, and C to be greater than 0. So everything needs to be positive. R can actually be any real number. R only shows up in line C. Everything else, B, A, and C have to be greater than 0. If we have multiplication on the inside, A times C, multiplying in leads to addition on the out. Oh, I am zoomed in a little too close for what I'm writing. Multiplication in equals addition out. Division on the inside equals subtraction on the outside. If you have the argument of the logarithm, a is the argument of the log b with an a in there, and it's raised to a power r, this is the same thing as pulling the exponent down and making it a multiplier. This one's trippy. And generally they show you how to do like the proof of these in many algebra courses. So the exponent becomes a multiplier. Line D is just a subset of line A if you look at writing that as c to the negative 1. So this is really a subset of that one. You rewrite it as a negative exponent, and then you pull the negative exponent up front, bam. This one is called the change of base formula. And we actually said F up above. This would probably be a lot easier on a class that had 1 hour a day rather than 50 minutes a day. Rather than trying to absorb all of trig and logarithms and exponentials in a 2-hour time period, or like refresh your memory, you could at least parse it over 2 days. Unfortunately, we're in 2-hour blocks. The other announcement I put up in case you missed it is test 1 has been merged into test 2. So we will not have a test next week. You use a lot of that stuff in chapter 1 in chapter 2. So there will be one less test. The overall extra credit is not going to change. Other than chapter 1 used to be worth 2% if you showed me your work, now it'll be worth 3%. That way, if you do everything by the end of the semester, you'll have 6% on the final. This is my way of incentivizing doing homework, rather than just slapping a big old percentage on the grade. And I made an announcement about it, and the syllabus is updated if you want to take a look. I post shit on Canvas announcements quite frequently, so hopefully you're checking them once in a while. All right. What the fuck? A web or something just fell on me. What is this bullshit? So these problems are a way of refreshing your memory about some of this shit as well. If we don't see a base, what does a missing base tell us about the base? Anyone remember? Ten plus to 1, add a 0 to it. So no base equals a base of 10. Now you can use the y equals log base b to the x and change that into x equals b to the y. So that would be the x stays the same following that principle. The b is our 10 and the y was our 3. So x equals 1000. Another way of looking at this is I'm going to just write log base b of x equals y. Show the general form of it. A way of remembering this is just take both sides and make them exponents of base b. So started with that, exponents of base b. And b to the log b cancels out. Because b is an exponential and log b is a logarithm. And they are inverses, so when you put them each other, they cancel each other out. So if we did that here, I need to zoom out a little bit. I'm just not giving myself enough room. If I applied this up here, I'd put a 10 there and I'd put a 10 here. That shit would cancel out. And this x equals 10 to the third power I see right there. When we see ln, what does that mean on problem B?
That's a natural log.
It means natural log, but what does that give us for a base? Yeah,
Log base.
log base e. So natural log or log base e. Rather than trying to juggle this formula, when I do this formula and I try to do it with the formula, I literally gotta go what's what and match everything up hella fucking slow. When I do exponents for both sides, this gets easy real quick. The e log e goes away and I have 2x minus 3 on the left and the right is e squared. For me, it's a lot easier to treat them as exponents of the base. If you're quicker doing this y equals log base b of x equals b to the y and working with this swapperoo of these two formulas, more power to you, but that shit slows me down. I'm doing this thing where I raise them to exponents. So e log e cancels. On the right side, I have 2 as an exponent on e. So 2x minus 3 equals e squared. E squared is just a number. 2.71 squared is less than 9. I don't know if it's greater than 8, but it's a little bit less than 9. The point is, it's a number. Let's not get excited about it. We don't need the decimal equivalent. We'll just leave it as e squared. It's a value. Solving for x, we add 3 to both sides. We have e squared plus 3. And dividing by 2, we have x equals e squared plus 3 over 2. Or you could write it as 1/2 e squared plus 3/2. All right, so on this one, we've got 3 to the x equals 7. Again, we can use that same rule over there, or the equivalent of my little cheat that I did right here with raising as the exponent. The other version is whatever this base is, use that as a log base of each side. So I'm going to do log base 3 on both sides. I don't know why I wrote it above. I think I'm gonna have hella room. Now, this is log base 3 of 3 to the x. And this is log base 3 of 7. We can use that rule where we pull the exponent down. X equals log base 3 of 3 equals log base 3 of 7. Not x equals log base 3, x times log base 3. That's 3, my bad, sorry. I wrote that funny. What is log base 3 of 3? It's just 1. When the inside matches the base, this is 1. So we get x equals log base 3 of 7. Some calculators do this pretty well, some don't. If you wanted a decimal equivalent, we can use the change of base. Your two options are doing natural log of 7 over natural log of 3, or you can do log 7 over log 3. Both of those are going to give the exact same values. The next example I am going to do a video of, but I want you to try to give that a try at home before I do. Try to figure out what this is. When I solved it, I had to use the quadratic formula at one point. And I even did a u substitution. So I did a substitution where I took out e to the x and just made it u. Give it a try, see what you come up with. I'll make the video. I'll try to get it done tonight. I think I can. I think I'm teaching a shorter class for my stats today, so I'll get out early and I'll be able to do it. Try to do that one at home and I'll make the video tonight and upload it. I want to show something else real quick that is not on this piece of paper related to limits. So, does everyone have that down? I know, you thought you were getting out. But one more thing. Well, two more things. Let's look at doing like the limit. Oh shit, I'm way too close. We're going to look at the limit as x goes to infinity of e to the x plus 1 over e to the x minus 1. Now, if you plug in infinity, like if you just like plug it in, this is e to the infinity plus 1 over e to the infinity minus 1. This is infinity over infinity, which is one of the indeterminate forms. Indeterminate forms. So this is where we like to pull out our magic. The easiest one to do on this one is multiply both top and bottom by 1 over e to the x. I think I'm going to need to do like a video for trig stuff on, because I didn't do any limits in 1.7 and I should have. If I distribute that, this becomes limit as x goes to infinity. E to the x over e to the x just becomes 1. And when we do 1 times 1 over e to the x, this is 1 over e to the x. When I do it on bottom, same thing happens, but there's a minus sign in there. If I look at plugging in infinity now, do I get an answer? 1 plus 1 over e to the infinity, 1 minus 1 over e to the infinity. This is a really, really big number on bottom. When you have like 1 over like 6 trillion, the decimal equivalent is basically 0. That goes to 0, that goes to 0, and we're left with 1 over 1, which is just 1. So the limit on that problem is 1. What happens if I go to negative infinity for the exact same setup? You may look at it and go, I want to jump to doing 1 over e to the x, but don't do it. Like, it's easy to get in the habit of trying these weird fucking things, doing conjugates and doing 1 over shit. Always try to plug in the value first. If I plug in negative infinity, I have e to the negative infinity plus 1 over e to the negative infinity minus 1. Now, you could rewrite these as 1 over e to the infinity. The other way of knowing 1 over e to the infinity, it goes to 0, is looking at the graph of e to infinity, or e to the x. E to the x goes like this. All of our exponentials did. We looked at that. So as x goes to negative infinity, y goes to 0. It's an asymptotic line. So that goes to 0, and that goes to 0. And we're left with 1 over negative 1, which is just negative 1. That's all I've got for you. If you've got any questions, feel free to ask. Otherwise, I will see you guys on Thursday.